Hi everyone, in this video we're going to talk about comparison tests, and this is section 10.4. And so what this is going to be about is two specific tests that are going to allow us to compare series that we're interested in to ones that we know about. So that's basically what I'm saying here. We can test the convergence of many series by comparing. So by comparing their terms to those of a series whose convergence is already known. So we are basically interested in certain series. We don't know a lot about it, but we can see how that series we're interested in compares to a series we already know some stuff about. And then we're going to start with what's called the direct comparison test, and then after that we'll do the limit comparison test. So here is our direct comparison test. Let the series of a sub n and the series using b sub n be two series with the following that must be true. They both have to be positive, so notice they're both greater than or equal to 0, or non-negative technically, but a sub n is actually less than or equal to b sub n. So b sub n is larger than a sub n. So that's going to matter because of the two statements here. And this is true for all n values. With that being true, then the following is also true. Part 1 says if the series with b sub n in it converges, then what do we know about the series of a sub n? Think about it. We're saying the larger series converges. The one that's bigger converges. So think of that as like a parent type function, or a better term would be maybe like a bounding function almost. And if this sounds familiar, we did go over this in a previous section on improper integrals. Okay, this came up with integrals. There was a direct comparison test there. So if the larger function is converging, okay, then the one that's smaller, like lower, if you could visualize it, must also converge. It can't go any higher than the one that's bigger than it. Okay, so if the series b sub n converges, then the smaller series a sub n must also converge. So also converges. Very much in the same manner, part 2, if the smaller series, series a sub n, diverges, then what does that say about the bigger series? So if the smaller series is like going to diverge, like let's say shoot up to infinity, then the one above it, the one that's always bigger, must also do the same thing. So if the smaller series diverges, then the larger series, b sub n, also diverges. Okay, so we're going to go ahead and look at some examples using this direct comparison test. Example, determine if the following series converges or diverges. The series where n goes from 1 to infinity of 5 over 5n minus 1. Okay, so as we're first learning this direct comparison test, it might seem like where am I coming up with the series I'm going to compare to? But what you'll see as you keep working on these, you'll be comparing to relatively the same ones often. Okay, so let me show you what I mean with this first one. Let's think about a series that we do know about, okay? Because that's the one we're going to compare to. We know about, and here's kind of how and why I'm going to pick the one I'm going to pick. We know about the series 1 over n. Okay, it's the sum of 1 over n. N goes from 1 to infinity. Okay. Now, why would I mention that one? Well, kind of how I went from here to here is I have a constant number on top. Here it happens to be a 5. On bottom, I just have a linear term of n. I just have a first power of n on bottom. The rest is just a constant here, constant multiple of n, just another constant in the back. So this can compare to this one, okay? Roughly, they have the same format. First power of n on bottom, constant on top. So this is a good choice for what we're possibly going to compare to. And then now, once we think, okay, maybe I should compare to this, we have to know how the two series relate. Okay, because then I need to know which one's larger, because that's going to affect what happens to the smaller one and vice versa. So how does, okay, the sequence that this series is based on, 5 over 5n minus 1, relate or compare, okay? Compare or relate, let's just add both words in there, to this one that we're interested in, 1 over n, okay? So what I'm trying to do at this point is figure out, well, which one of these would be larger, which one of them would be smaller, okay? So I'm going to take my existing sequence that I'm using for this series, 5 over 5n minus 1, and we're going to apply a math tool. Let's see if you can figure out which one. Math tool, multiply by 1. So we're going to multiply by a funny looking number 1, and it's going to allow us to rewrite what we have in terms of this 1 over n. It's going to look more relatable. So the number 1 that I'm going to pick is 1/5 over 1/5. Remember, that's 1. I'm dividing the same number by itself. Why I pick that is because it's going to get this 5 on top to turn into a 1, and this coefficient on n also is actually going to turn into 1. And so if we just multiply this out, on top we're going to get 1. On bottom, the first term is going to be just n, and then minus a 1/5. So then, what do I know about this 1 over n minus 1/5 and 1 over n? Okay. Eventually, you'll start to get a feel for the relationship between things like this, but let me just guide you to it. This has the same denominator, other than this one is getting something subtracted, right? So this number, n, is actually larger than n minus 1/5. Whatever n is, this is 1/5 less than that. So think about fractions. If I had 1/2 and 1/3, the smaller denominator, okay, if I take away something, the smaller denominator is actually a bigger value. 1/2 is bigger than 1/3. Do it again. 1/4 and 1/3, well, again, the smaller denominator makes the quantity larger. 1/3 is bigger than a fourth, and so on. So this quantity is less than this one. 1 over n, take away something, is actually bigger than 1 over just n. So we know this is how these two sequences relate. This one is greater than, or technically it could possibly, no, I was thinking it could be equal to, but it won't. It's strictly greater than, okay? Strictly greater than 1 over n. All right. So just to make it very clear, we had our criteria for our direct comparison test. It said that both series had to be positive, but one of them had to be larger. So the larger one, just to reference our test that we wrote down, we were calling it b sub n. So b sub n is greater than a sub n. And if this notation is weird for you, you can just flip the way you write it, and it says a sub n is less than b sub n, if that helps. Okay, so now let's see, what do we know about the series with 1 over n? Okay, so let's erase this. Okay, back here I said we know something about that. Let's recall what we know. This was, in the previous section, this was a p series, but if you remember specifically, this was the harmonic series, okay, when p is invisible 1. And by any p series, where, let me just write it for you, when p was less than or equal to 1, that series diverged, okay? That was when we had 1 over n to the p. Okay, we just talked about this in the previous section, p series. Specifically though, this one had the name harmonic series. This series diverges, okay? We know that this series diverges. Okay, so how does that relate to our series? This is saying the smaller series diverges. Therefore, the series bigger than it, the smaller one, diverges, so the series that's above it, bigger, also diverges. This is part 2 of the comparison test. So we can say something like, since the smaller series, we called it a sub n, okay, so let me be very specific here. Since the series with a sub n, in our case it was a series 1 over n, when n went from 1 to infinity. Since that one diverges, the smaller one diverges, then the larger one has to diverge as well. So we called it B sub n, series with B sub n, which in our case was 5 over 5n minus 1 also diverges. Diverges. And that is what we were trying to answer. And so we used the comparison test, direct comparison test, to make this conclusion. Okay, let's go ahead and try another one. Next example, determine if the following series converges or diverges. And we have the series where n goes from 0 this time until infinity, and then we have 1 over n factorial. So let's just first see what some of these terms look like in this series. So this is 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, and so on. Let's just get a handful of terms here. Let's see, 1 over 4 factorial, and we'll go 5. Hopefully that's good. Now, if you don't know about factorials, just so you're aware, it's that you add up you multiply, by the numbers below this number that's listed. The exception is 0 factorial. 0 factorial by definition is 1. So this is actually 1. 1 factorial is 1. It's just 1 times itself. So that's 1 over 1. 2 factorial is 2 times 1. So this is 1 over 2. 3 factorial is 3 times 2 times 1. So this is 1 over 6. And then 4 factorial, 4 times 3 times 2 times 1 is 1 over 24. 5 factorial, 5 times 4 times 3 times 2 times 1. That's going to be, 120. And hopefully that's enough to be able to figure out some stuff about this series. So we know about, let's see about a series that we think might relate to this one, that we know something about. And again, for this first example, these first couple of examples, I'm going to show you ones that you might have thought, like, well, how did I know to pick that? Well, eventually you'll start to see similar types of choices when you're working on these problems, and you'll recognize, okay, I should probably pick this type of series to compare with this type of series. So the one that I'm going to say we know about is actually this one here, the series when n goes from 0 to infinity of 1/2 to the nth power. So this one, let me show you why I picked it. I'll show you when we answer the next question. But let's just identify some terms in this series really quick. This is in fact a geometric series, so that's why we know about it. We talked about those a few sections back. But when n is 0, that's just 1/2 to the 0, which is 1. When n is 1, that's 1/2. When n is 2, that's 1/4. N is 3, 1/8. N is 4, 1/16, and so on. Okay, so we know that this series, we actually know about its convergence or divergence. I'll mention that in a little bit later, but I just want to show you what the series looks like first. Okay, so the question now becomes, how does our series 1 over n factorial relate to 1/2 n, to the n power, excuse me. And so you can kind of look a little bit at what I have already written. First term is 1, second term here is 1, but then we have a 1/2. Okay, so far they're equal. Then this term is less than this one. Then 1/2 here, 1/4 here. Okay, now this one's, am I on the third one? Yeah, so now this one's less than this. Okay, 1/6. Okay, 1/8. This one's less here, 1/24, 1/16, but now this one's less than this. Okay, so it's kind of swapping, like this one's less sometimes, this one's less the other times. So we need it to be consistent, like one of these series is always larger than the other one. So here's kind of a a trick that I'm going to use here. The fact that there's 2 1s at the front of this series, I'm going to take our geometric series here and I'm going to actually just shift it. Okay, so I'm answering how do they relate. Let's shift this geometric series over so that there's still another 1, and I'm just going to just add that extra 1 in there. So let me get rid of this stuff really quick and put in what I'm saying. Okay, so I'm going to erase this and leave a space. I'll put it in another color. I'm going to go ahead and just add an extra 1 in here. And so this series is still these terms here, but I'm kind of like shifting it over because I'm adding in an additional 1 at the beginning of it. And so now what that's going to allow us to do, and you know what, let me line it up even better. I want you to see it more clearly. Okay, now all of that, what I'm talking about, here's the point. Now let's relate these two series. Let's see if it's consistent, like 1 is always larger or equal to, or 1's always smaller. So equal to, both series have a 1. 1, equal, equal. So far, terms are equal. Next position, fourth term. The 1/6 is less than 1/4, so 1/6 is less than this one. 1/24, that's smaller than 1/8. 1/20th, smaller than 1/16. And 6 factorial is going to make that one smaller than 1/32. So this is actually going to be smaller than or equal to this series. All right, so we're answering that question. How do these two relate? So what we have is that 1 over n factorial is always less than or equal to 1 plus 1/2 to the nth power. Okay, there it is. So let's see, let's clarify. We call the smaller one, just from our direct comparison test, we called that one a sub n. We called the bigger one b sub n. And then now we're ready to determine what we know about the one we said, hey, let's pick this one. What do we know about it? And so recalling from when we learned about geometric series, let me just write that information over here. So we had learned a few sections back when we were talking about infinite series, when we were just getting into it. We learned about geometric series, and for a geometric series that had the format, let's see, a times r to the n minus 1, and this was when n started at 1, going to infinity. We know that this converges, this series converges anytime r was less than 1, or because it's absolute value, greater than -1. Okay, so when r is between 1 and -1 is basically what this is saying. It diverges otherwise. Okay, so look at what we have. Our r value here for this series is a 1/2. Well, 1/2 is less than 1. Okay, so we know that this series converges. And then just a quick reminder from when we learned about this, we actually know what this converges to. It converges to a over 1 minus r. We went over that a little bit in another section. So this converges to a, which is an invisible 1 here, divided by 1 minus 1/2, and then we're just going to add a plus 1 to that. So this is just some number plus 1. It's going to converge. If you want to calculate it, if you want to check yourself, it's going to be 3. This would converge to 3, just so you know, if you plug in the numbers there. But the point is that we know that this converges, and this one is the larger series. So if the larger series converges, then the smaller one must also converge. It can't go in, can't pass it. It must also converge. So by our direct comparison test, we can say, since 1 plus our series that's geometric with r equal to 1/2 as n goes from 0 to infinity, since this one converges and it's the larger series, then the smaller one, series of 1 over n factorial, and goes from 0 to infinity, also converges. Okay, so we were able, converges. We were able to use our direct comparison test to figure out that this series converged. So just a quick note, in the future, you'll start to see similar things that, series that you're going to pick kind of often. The first one we did was a harmonic series. Another one that you're going to see a lot is a geometric series. Maybe not 1/2 to the n, but another geometric series might come up a lot. So just some options for you to compare to. We're going to take a look at another test now for convergence or divergence. It's called the limit comparison test. Okay, so we technically learned this in terms of integrals in a previous section, so this should look somewhat familiar as far as recognizing some of the ideas here, okay? But we're doing this for series. So suppose that a sub n is a positive sequence and b sub n is also a positive sequence for all n's greater than some integer value capital N, okay? Now there's three possibilities with this limit comparison test. Possibility number one, and notice all three possibilities have the same starting point. If the limit as n goes to infinity of the quotient of a sub n over b sub n. So if you divide a sub n and b sub n and you take that limit as n goes to infinity, then three different possibilities based on the answer. So if you take that limit of the quotient here, if you get a number, and if that number is positive, okay, then the following is true. Then both series converge or both diverge. They behave similarly. So if you take this limit of this quotient, get a number, it's positive, then the series act the same. So you are basically comparing again to a series that you know about, and so maybe you will know about b sub n, maybe you will know about a sub n. Normally we know about a and we pick a b sub n, and then we base on that. However, the series with b sub n acts, a sub n would do the same, or vice versa. They both converge or both diverge. Part 2. The limit as n approaches infinity of the quotient a sub n over b sub n if you get 0. Okay? If you get 0 and the series of b sub n converges. So if the series that you're using for the denominator converges, then the series a sub n also converges. And that happens when the limit is 0. Third possibility. You take this limit as n approaches infinity of the quotient a sub n over b sub n, and you get infinity. Okay, this limit does not exist. It goes to infinity. It's an infinite limit. If that's true and b sub n, this series, diverges. So the denominator, that series that we use for that denominator, if that one diverges, then we can conclude the series a sub n also diverges. Okay, so for this one there is 3 parts, and you kind of have to start, well, you actually have to start the same way on all 3, based on the answer to the limit. Okay, 3 answers to the limit, then you conclude what you can about the series you're actually working on. Okay, so let's try this one out. Example, determine whether the series converges or diverges. Okay, we have the series from n goes from 1 to infinity to n plus 1 over n plus 1 quantity squared. Okay, now we are going to have to find a series to compare this to, but I'm going to show us how to get there. The very first thing I'm going to do actually is I'm just going to rewrite this to see if it helps. I'm going to expand the denominator. Okay, so I'm just going to FOIL out the denominator. So we have 2 plus 2n plus 1 on top. FOIL out the bottom, you're going to get n squared plus 2n plus 1. So I'm going to call this a sub n. So we're going to say, let's go ahead and let our sequence a sub n be this right here. So this expression 2n plus 1 over n squared plus 2n plus 1. Now what we're trying to now figure out is what's a limit, series to compare this to. Technically a sequence, because I'm just going to think about b sub n as a sequence. But how I'm going to get there is figure out how does this actually behave when n goes to infinity, because I'm going to take the limit eventually. This is going to use the limit comparison test. So my question is, how does a sub n behave as n gets like really large, goes to infinity? As n gets big, gets large, big numbers. So let's think about it. So this sequence here, if you plug in something huge, plug in a very big number, okay, the top is going to be 2 times that, the bottom is going to have that number squared plus 2 times that number. These little plus 1s in the back, they're not going to have much effect at all. If a huge number plus 1, not going to do a whole lot to it. So I'm going to say that this is approximately the same as 2n on top, n squared plus 2n on bottom. Those plus ones are negligible. Okay, let's keep going. If I factor out an n from the top and bottom, I'm going to get a 2 on top, n plus 2 on bottom. Again, I'm thinking about as n gets really big, what happens here? If n gets really large, if I plug in a big number here, if I add 2, not a big impact. Not going to change that value by very much. So this is similar to 2 over just n. That plus 2 is not going to make a big difference for really big n numbers. So what I'm thinking about now then, my B series or sequence in this form, it's going to look like this. Okay, so here's what we're going to do. We are going to let B sub n, I'm going to pick 1 over n. B sub n is going to equal 1 over n. Now, I could have just taken this 2 over n, and I'm going to make it clear that you can do that. So note, we can choose for B sub n to be 2 over n, and you're going to get the same result. I'm just choosing 1 over n because we know a lot about that, and it'll just make our calculations just a little bit easier. So it doesn't matter. Pick 2 over n, pick 1 over n, we will get the same results. Okay, but we have a constant over n, so this is going to behave similar to this. Okay. All right, so now we are ready for the limit comparison test. These are both positive sequences. Let's compare the limit of their quotient. So what the limit comparison test says is to take the limit as n goes to infinity of a sub n over b sub n. So let's do that division. N goes to infinity. So I'm going to write it all the way out so you see all of it. 2n plus 1 over n squared plus 2n plus 1, that's a sub n, over b sub n, which I'm saying is 1 over n. Okay, let's do a little bit of algebra here. I won't keep writing limit. Let's just work on the algebra. I'm going to flip and multiply by this n over 1. And so we're going to get 2n squared plus n when I flip and multiply by n on top over n squared plus 2n plus 1. Okay. Now we are taking the limit as n approaches infinity. So from the past, we know that a technique for taking these infinite limits is, or limits approaching infinity, is to divide by the highest power of n from the denominator. So I'm going to take all these terms and I'm going to divide by n squared because that's the biggest power of n on bottom. So n squared on every single term here. Technically I'm timesing the top and bottom by 1 over n squared to be able to do this. Okay, so then we get, let's put the limit back on. We get the limit as n approaches infinity. We have 2 plus 1 over n, that's the numerator, 1 plus 2 over n plus 1 over n squared. Okay, now let's see. We know some stuff about what's happening here. We're going to apply this limit. We're going to take this limit. As the bottom gets really large, 1 over infinity, this is going to 0. 2 over infinity, going to 0. 1 over infinity squared, going to 0. So we end up with this limit equaling 2 over 1, which is just 2. And this is positive. Okay, so if you look back at your notes maybe from just a couple minutes ago, this was part 1 of your limit comparison test. Okay, part 1 said if your limit of this quotient equaled a number that was positive, then both series either diverge or both series converge. Okay, so now let's go back and see what we knew about the series we compared to. Okay, so let me just erase a little bit of stuff really quick. Okay, we compared to b over n being 1 over n. B sub n is 1 over n. So let me say what we know. We know the series, as n goes from 1 to infinity, of 1 over n. That was our b sub n choice. We know, we've seen this one over and over, we know it diverges. This is the harmonic series, or p series when p is 1. This one diverges. So let me make it very, very clear. By part 1 part 1 of our limit comparison test, just to save some writing. Limit comparison test. Then we can say, let's get this out of the way. Then our series, since this one diverges, this equal to a real positive number, then our series also diverges. Okay, let me just put our series in here really quick. 2n plus 1 over n plus 1 squared. Okay, and that is what we were trying to determine. And that is our first example for limit comparison test. All right, let's try another example. Again, are we going to be working with a convergent or divergent series here? We have the series starting from 2 this time to infinity of 1 plus n natural log of n over n squared plus 5. Okay, so we are going to call this a sub n. So we're going to let a sub n be the sequence 1 plus n times natural log of n divided by n squared plus 5. We are trying to find another sequence here that represents a series eventually that we can compare this one to. So we're going to try the same approach as the last problem, where we kind of figure out, well, how does this behave as n gets big? Okay, so as n, I'm just going to say approaches infinity. So as n gets large, this sequence, look what happens. This plus 1 becomes negligible, so does the plus 5. You have really big numbers, plus 1 plus 5 doesn't really make a big difference. So this is similar to n times natural log of n over n squared. Okay, or multiplying here by an n in the front. This is natural log of n. That one is, you're taking the log of it, but this n is being multiplied. So we can divide out an n. We have natural log of n over just n. Okay, now from here there's not much else we can do, so we kind of have to think about what could we possibly compare to at this point. And what I'm going to say is we should compare to 1 over n again, our harmonic series. And it has to do with the single power on n down here. We just have n in the denominator to the first power. And natural log of n, it is going to change. It is going to assume different values depending on n. But let's see what happens. So I'm going to go ahead and let b sub n be 1 over n. Our harmonic sequence, which is going to become our harmonic series. And so let's compare. Right now I don't know exactly how they relate, but let's just identify for a few values. So just some observation here. N is, we're going to start at 2. So let's say when n is 2, and we have, well, let me make a table kind of here. ln of n over 2 and 1 over n. Okay, so when n is 2, sorry, this is an n. We have natural log of 2 over 2. Okay, let's figure out what that is. And then over here we have 1/2. Okay, when n is 3, this is natural log of 3 over 3. And over here we have 1/3. Let's just do another one. When n is 4, natural log of 4 over 4. And this is 1/4. Okay, let's see what these values are. We get 0.34 here for natural log of 2 over 2. We're going to get 0.37 for natural log of 3 over 3. We're going to get 0.35 for natural log of 4 over 4. And you know what, let's do another one. When n is 5, natural log of 5 over 5 is about 0.32, and this over here would be 1/5. Now let's compare, let me give some decimals over here. We know 1/2 is 0.5, 1/3 is about 0.33, 1/4 is 0.25, 1/5 is 0.2. Okay, so let's do a little observation about what's happening in comparison. Over here, 0.3 is less than 0.5, okay. 0.37 is more, okay, more than 0.33. 0.35 is more than 0.25. 0.32 is more than 0.2. And if we keep going, these are going to always be bigger than these ones, the 1 over n. So just on the first one, it wasn't less than, it wasn't, this one wasn't greater. But if you wanted to test it, if you kept going, these ln n over n, is going to be greater. Okay, so what we have here is that starting at n is 3, so for n is greater than or equal to 3, we know that natural log of n over n is greater than 1 over n. Sorry, looking at what we have. Greater than, we'll say greater than or equal to. Okay, now we, of course, we want to consider this first point where it was the opposite of what we just said, but we are trying to approach infinity, and so we can actually make assumptions about the rest of it, because just after this very first term, everything on the left is the bigger one. ln of n divided by n is always bigger. So we're going to say that this is true in general. Yes, it technically starts at 3. All right, so what do we know about this series really quick? So the series, we know, we can start at 2 here, even though 3 is when this one was bigger, but as you approach infinity, we're going to be fine to start at 2, just like this starts at 2. The series of 1 over n, our harmonic series, we know that this diverges. Okay, this is our p series with p equal to 1. This one diverges. Okay, so we know this. All right, just kind of box it in a little bit. So let's use the limit comparison test and see what happens. So the limit comparison test, we are going to divide a sub n by b sub n. Okay, so applying our test. The limit as n approaches infinity of a sub n, which is that, 1 plus n times ln of n over n squared plus 5, divided by b sub n, 1 over n. Okay, let's start simplifying. So I'm just going to do the algebra real quick. Flip and multiply. We're going to get times n on top. So n plus n squared times natural log n over n squared plus 5. Okay? Very similar to the last one. We are taking the limit as n approaches infinity. So let's divide all the powers, or all of the terms, by the highest power of n from the bottom. So divide by n squared on all of these terms. Divide by n squared. No, it's a little hard to see. I'm just dividing everything by n squared. Then, let's put our limit back on. The limit as n approaches infinity, this is going to be 1 over single n, 1 over n. This n squared divides out, so this can be plus natural log of n over, this is n squared by itself, so divided by itself, so 1, and this is plus 5 over n squared. Okay, let me move this up so it's not in the way. As n approaches infinity, what happens? This term is 1 out of a huge number, that goes to 0. Same thing here, okay? But even though we have 0 plus this, and over 1 plus 0, what happens here? As you plug in a really big number, natural log of a big number equals a big number. So this term is going to infinity. And so we actually have like infinity over 1. This limit is diverging. It's going to infinity. Okay. So what do we know? We know that we are actually working with part 3 of our limit comparison test. So part 3 says that if this limit equals infinity and b sub n, the denominator from our division, diverges, so both of those things are true, this is true and this is true, then by this test, by part 3 of our limit comparison test, then our series also diverges. So our series 1 plus n natural log n over n squared plus 5 from 2 to infinity also diverges. All right. So a lot of the times you will compare with 1 over n, not always. You might compare with a geometric sequence like we did in the direct comparison test. So there are different series that you'll compare with, but you'll start to get a feel for that. All right, and that's it for this section.